Hello, welcome to my presentation. My name is Faramarz Nilfouroushan. I'm a geodesist at Lantmäteriets. I work with GNSS and InSAR, mostly for crustal deformation analysis. And I also work at the University of Hjälp as a senior lecturer in applied geodesy. And today I'm going to talk about establishment of a new geodetic infrastructure using InSAR corner reflectors. And this is based on the ongoing project, which started last year, October, and it will end by the end of next year. And in this project, as you can see, there are many organizations, and the project is led by Rymdstyrelsen, Swedish National Space Agency, and there are other organizations that they are collaborating, and Lantmäteriets is one of the collaborators which I'm coming from. And at Lantmäteriets, there are other colleagues. There are many colleagues behind this collaboration working with me, and they are helping in this project. So the project, you have heard from other colleagues that this is about ground motion service of Sweden based on InSAR technique, which is a remote sensing or geodetic technique. And we can measure very accurately the ground motions with the millimeter accuracy. And we can make time series and do lots of analysis for different applications. So the goals and work packages, there are many different goals and applications that we are working on it. And the main goal is providing a deformation map for the whole Sweden, and making the time series and highlighting the deforming zones, and also to distribute this information to the potential users and find the areas of interest. And as you can see, there are different work packages in this project. And the main work package is project administration by Rymdstyrelsen. The deformation data is provided by NGU, that they are processing the Sentinel-1 data, and they use PSI technique, and they provide this average deformation map and also the time series, which you can see. This is an example, for example, for Kiruna to the right. The total measurement point for the whole Sweden is 1.5 billion points. And on these measurement points, we can extract the time series. We can see the movements, and we can track that over the time, for example, between 2015 and 2021. And that's great, actually. This is fantastic to see that how the deformation is happening and in which locations. And then we can make warnings, analyze the risks and many other applications. And in these different work packages, you can see in the third work package, here Lantmäteriets comes and contributes mainly, and that is the validation of deformation data. And when we are talking about the validation of the data, there are different types of validation. It can be by field observations, it can be by in situ measurements, geotechnical or geological or geophysical measurements, that we have some deformation, but is it true, how much it is? And then we have some type of measurements, geodetic measurements, for example, leveling, GNSS, and other techniques that we can cross-correlate and see if they are valid, if they are reliable or not. And also there is another way to compare these results with the previous studies, if there are any. And this is one of the things that Lantmäteriets so far has done. And we published the two papers and studied the subsidence in two cities of Sweden, Uppsala and Gävle. And in these papers that you can see, they published in remote sensing. This is one of them for Uppsala. So there is a problem for subsidence that the city, part of the city, is lying on the clay layer, post-glacial clay. And clay layer is a weak layer, and we have a subsidence up to 6-7 millimeter per year. And this is interesting. To the left, you can see this is the results from our study with my student Jonas Frixten. You will see the distribution of the deformation, mainly in the center of the city, and the rate of deformation on these measurement points. The reddish part, they show the subsidence zones and also the rate. As you can see, there's a color scale, -5 or -6 to 5 millimeter per year. And that shows how fast is deformation is happening. And the interesting thing is, this is a Pareto study, independent study, and now we are coming to this Swedish GMS, which we have today. And that Swedish GMS now also shows exactly the same, the distribution and localization of the deformation, and also the rate that we can see. This is the same color scale for the deformation rate. And here we can also see it is 5 to 6 millimeter per year in those deforming areas. In another study also we did with other colleagues, Mohammad Bagharbandi and Nuruddin Guido. So also we published in Remote Sensing, and it's open access. You can read it more. But interestingly, we wanted to just see how it looks like, what we did and what we get from this Swedish GMS. And interestingly, for Gävle City, so mainly you can see that to the left, this is our study. So the localization of deformation, it is just happening near the harbor, and most parts of the city, they are stable. The green means no movements, it's almost stable. And the coming to yellow or reddish areas, it shows the rate of the movements 5-6 millimeter per year. And this subsidence that we get, actually, now we are coming to this Swedish GMS. And this is done by NGO and with their own developed programs and softwares, and the data set and parameters that they have tuned. But finally, we are coming to the same conclusion that this is the localization of deformation and this is the rate, and they agree very well. So this can be also a kind of validation we have done with comparison with other studies. But so there are also other types of validation and thinking about future, how we can make it. And it's good to notice that InSAR is very useful for geodetic infrastructure. And as you know, I mean, one of the main tasks of Lantmäteriets is defining and maintaining the geodetic infrastructure, which is very important, for example, for geodata quality and accuracy. So InSAR, which is measuring the movements very accurately, therefore it helps in this respect, because in the right you can see this is the Swipos GNSS reference stations, and this is more than 400 stations all over Sweden, and these are permanent receivers that they just collect the data. We can calculate the position and also the velocities of these stations. And it is important to know that these stations, they are stable, or if there are any local deformations happening around these stations. And therefore, InSAR can help to separate different signals, if this is a plate tectonic signal or this is a local deformation, how they combine these signals together and separate these signals from each other. And as I said, this is an example of geodetic infrastructure, a physical one. But we have reference frames, we have tide gauges for sea level variations, and also we have leveling benchmarks, we have gravity points. So all these measurement points, which are important for geodetic infrastructure, so they can be also, I mean, in the process of a deforming zone, and so that's also important to monitor them. But InSAR also is useful in that respect. And then we can talk about, as I said, I mean, if there are the signals, the deformation signals, they are combined and useful for linear and non-linear movements, which we can see the time series of the movements over the time, over 5-6 years. And if sometime it was stable and suddenly it's going down, so it's not exactly linear, so we can separate this stable period and also deforming period from each other. And there are also other processes and applications that we can use it for glacial isostatic adjustment. So when we are doing these deformation models, so we want to have our reference frames stable and remove that deformation signal, which is about 10 millimeter per year. I mean, in the center of uplift that it's happening, and that can affect all these coordinates of our benchmarks. And therefore, we need a deformation model coming from this glacial isostatic adjustment analysis. And InSAR can help if there are any localization of deformation at some places. It is not GIA, but it is something else. Then we can try to separate these signals. So also about crustal deformation, if something, any local faults and so on. So if there are any effects. And also hydrological loading signals. If the underground water is fluctuating, so how much it can affect the compaction and also the subsidence. So that is also important, or even uplift. So those kind of signals also can be derived from InSAR and then correlate with the data we have from hydrological models. And then it's important, we are talking about geodetic infrastructure or tide gauges. They are along the coast. And then we are talking about sea level predictions and measurements. And the coastal levels also, they can have erosion. They can be, deformed. And InSAR can contribute to that kind of studies as well. And InSAR is working based on the radar, transmitted radar from the satellite, from the SAR sensors to the ground. And then we make this distance in different time. We measure this distance. And if this distance is getting longer or shorter, so it shows the subsidence or uplift in the line of sight. And actually, to have reflection from the surface, the properties of the object on the ground is important. So we cannot get the data, the reflection from the radar everywhere. We have limitations with this technique. So in the forest area, in the vegetated areas, so we have no data. And in some places, like in the cities, we have buildings or we have power towers. And you can see that, if you can see to the right, we have a graph showing the signal strength and also the range. And you will see that there are some of these reddish places, they show very strong signal. And those signals, they are coming from these high reflective objects. And this is what we expect, that in the cities, mostly we get higher density measurement points. And when you go to outside, it's just roads and railways, and so that, we can have those measurements. But also there is another one, distributed scatterers. The signal is weak. We can track them sometimes, not always. But the good point is these natural permanent scatterers, we can distinguish them in all images, and we can have a data set and track and make a time series in different measurement time. And imagine if you don't have any natural reflector, then you need something to measure at the desired location. Then you go and install an artificial reflector. And that is called corner reflector or InSAR reflectors, which we are going to make it as a geodetic infrastructure. So we go for radar reflectors, and these are the artificial ones, which is the focus. And why we install them, as I said, we can improve the spatial sampling in those areas that you need the measurement points. Then you go and install these ones, and you try to track them in different images, do interferometry, PSI technique, and make a time series and talk about deformation. And then it is useful also to connect InSAR and other techniques. So for example, if you have different images and they have overlap and your corner reflector is in between, then you can also make a link between different frames. And also, if you have different satellites, for example, TRASAR or Sentinel, and then you have different images measurements, this common reflector make a common PS, and then you can make some kind of link between what you get from different systems. It is important also to know, and this is one of the main things for the validation of the results of this ground motion service, and that is to connect between GNSS, which we have permanent GNSS stations, as I showed you in our reference network, SWIPOS. So they make a time series all the time, daily base or hourly base, so we can have these measurements. And if you have also the same, a time series from InSAR, so you make 2 time series, and then you can compare and correlate the results. And what we get from InSAR is a relative. Then using this well-defined coordinates and velocities from GNSS, we can make our InSAR products absolute and define and realize a reference frame for that. And then calibration of satellite imagery systems. For example, ROSE-L and NISAR, they are coming. So these are the future missions. And then we need also to have some kind of calibration, and it has been also in the past for other systems like Sentinel-1. So these are some examples of radar reflectors applications. To the right, you can see that, for example, in the Corvera, in Alps, in Italy, so there has been an ongoing landslide. And this is from the paper Darvishi et al. 2018. And because they didn't have any natural scatterers, so they went and designed and placed some artificial reflectors, which you can see to the right of that picture. So these are the corner reflectors. These are kind of metal plates orthogonal to each other, and based on which type of satellite we are using, we have the type and size, different types and sizes of these reflectors. And they will be artificial reflectors that when the satellite passage we have, then they can reflect back very strong signal to the satellite, and we can track all over the time. And talk about the landslide that is happening and the rate and distribution of that landslide. And this is another example from Norway to the left. And you can see Norway, I mean, now they have established, they have installed many of these corner reflectors for different applications, but mainly for rocket slide movements. And at some of these corner reflectors, they have also GNSS. And you can see very interestingly that how correlate, how well the results of GPS movements and also the InSAR on this graph, that the blue shows the GPS measurements, and in the black you can see the InSAR results. And this is the millimeter, the displacement, and on the horizontal axis you can see in different time between 2010 to 2014. And the trend and also the behavior of that time series, you can see that it correlates very well. And that is actually the beauty and also the very good thing with these corner reflectors, that they make such a very precise measurement points on the ground. And as I said, I mean, there are also other applications. And in the bottom, you can see a corner reflector newly installed in Oklahoma. And this is for new coming NISAR mission. And the size you can now see from the scale of how many people they are standing there. It is 2.8 meters inner leg of that trihedral triangular corner reflector. And that is for calibration of this system. So when we are talking about corner reflectors, there are different types. There are passive ones and active ones. In the passive ones, which you can see on the left, they don't have any electronics, no power. And then we orient toward the satellite these corner reflectors. We know the azimuth and the elevation of the satellite at the passage time. So we know that when they are coming, we calculate that, and then we orient the corner reflector toward the satellite. And then there is another type. These are electronic ones that there are ascending and descending antennas. So they receive the radar and they amplify and they return it to the satellite. So we know that exactly when the satellite is coming, we configure this electronic corner reflector, or the so-called transponders. And then we know that what's the time and how long it should be activated. So it will be alert when the satellite is passing, then it receives the signal and then amplify the signal back to the satellite. And we get a very strong signal. And to give you an example and get a feeling, so you can see on the right that before and after installation, this is a backscattered image from Sentinel-1 in different time before and after installation of a corner reflector, or here a transponder. So you see that this is a kind of salt and pepper. I mean, there is no so much bright pixels in this one, in the bottom part. But in the upper one, you see that this is after installation, and you get very, very bright spot in the middle. And that's a strong signal provided by the transponder, which we can track in all these subsequent images, and then make a time series how the point is behaving and deforming and moving. So when you are talking about passive corner reflectors, which they don't have any electronics, so then it comes to which type of satellite we are using. Is it Sentinel-1? Is it InSAR? And they have different frequency and wavelengths. And then there is an important factor which we consider, and that is the RCS. And RCS is the ratio of the energy transmitted and reflected back from the object. And if this ratio is getting higher and higher, we can go to the millimeter accuracy or even fraction of millimeter accuracy for the displacement measurements. And these RCS values, I mean, depends on, you can see in the left, we have different types and sizes of these reflectors, trihedral triangular one, or a squared one, or these circular ones. And this A is the inner leg, the dimension. We can go, for example, for 1 meter and 1.5. I mean, when you increase this size, this length, then you provide more surfaces, a bigger surface, which they can reflect the signal in the corner reflector, and then parallel to the incoming signal, it can go back to the satellite. And today we are using this, for example, one of the corner reflectors now we are working at Lantmäteriets, and now we are making more. One of these triangular ones, 1 meter inner leg, and also we are working with these squared ones. And this is, firstly, we should consider which satellite we want, and then we select the proper corner reflector, and then we should orient it in the field for the azimuth and elevation, and then we just leave it in the field, and it will be our measurement point. So no need to, visit the field, no need for transmitting the data. Everything is coming automatically in the SAR images recorded in the satellite. And then you can see when we have these corner reflectors, they can be oriented toward ascending or descending orbits. So we have the satellites, they are orbiting, and we have ascending and descending the directions, different directions. And when we are orienting these corner reflectors for the satellite, either ascending or descending, then they can provide the LOS measurements. And these LOS measurements, when you see the picture in the left, you can see LOS measurements from ascending or descending. When we mix them, we can talk about vertical component deformation and also east-west component. But unfortunately, because the orbits of these satellites, Sentinel-1, they are polar, so they are not very sensitive to the north-south component. So we mostly get east-west and vertical component. And that is one limitation of this InSAR technique, but still, I mean, it provides lots of very useful information. And ascending and descending, therefore, we can have our corner reflector and track just one geometry, and then project it for the vertical. But also we can have a mixture of both ascending and descending. You can see to the right either electronic ones or, I mean, these passive ones, this rectangular one that you have GPS antenna on the top, in the bottom picture. And then they provide both ascending and descending measurements, and we can combine and project them in different components for deformation signals. So now, I mean, using these corner reflectors, we are going to establish a CR network, corner reflector network in Sweden. And this will be a new geodetic infrastructure, actually, because we have, as I showed you, we have GNSS, we have other geodetic infrastructures, but this will be based on InSAR, for InSAR application. And the first plan and first discussions we had, so we have planned for this 21 Class A permanent GNSS stations distributed, as you can see in this map. And these are fundamental stations that they have a long history of the data. And they are installed on the bedrock, so they are very stable. And the plan is to co-locate our corner reflectors with these GNSS stations. And the good thing is, when we co-locate these reflectors with the GNSS, just a few meters or tens of meters, then we can have a time series from GNSS, and that time series over the time, the changes of the coordinates over the time, which gives us the velocity, we can also get from these corner reflectors, similar to the one I showed you from Norway. That one time series from InSAR, one time series from GNSS, and therefore they can be correlated and they can be studied together. And that is very important, this co-location of different techniques, and then for validation it is important. But also it is important for calibration of Swedish GMS and in future, because still, I mean, when we install it today, it takes some time to come to the picture for the Swedish ground motion service and also even for European ground motion service. But this is investment for future, that we are installing this geodetic infrastructure, and then we make benefit in coming years with Sentinel-1, ROSE-L, and other things that they are coming, and we have already started this time series. And this is good for calibration, as I said. So these InSAR products, they are relative. They want to define a good reference frame. They want to make it absolute. And therefore, if we know the time series of the GNSS, we can have also, sometimes we have PS points, natural reflectors, but sometimes not. But the good thing, when we install that one, there is a guarantee that we get a measurement point just near the GNSS stations. And we can correlate them, we can align the time series, and we can calibrate the products. And the good thing is this is also something for future, that when we install these corner reflectors at different places, and also neighbor countries already, they have started or will come to this also activity, so we can make a regional network in the Nordic countries. And I know that, we know Norway has done for this some local deformation studies. Finland also is coming, and already Denmark, they have installed some of these transponders and corner reflectors. And that's very promising that, all these countries all together, so we are making more and more these artificial reflectors. So the transponders, these active ones I mentioned, so that's good that we got some experience through a project, InSAR project, and that was for height system unification in the Baltic Sea. So in the right picture, so you can see that different countries, they were involved in this project, and they installed these transponders around the Baltic. And we got some experience how they work, what are the limitations, and what are the problems, accuracies, absolute positioning with these ones. And we published the results, the initial results in this remote sensing paper. If you are interested, you can go and read more. And the good thing is, during this project, we installed 3 of these reflectors, transponders in Sweden, in Lantmäteriets near Sundsvall, and also in Morsbo near Gävle, and also in Forsmark, which we have a tide gauge. So they started last year, and some of these ones, one of them is near the tide gauge, and the others, they are near the permanent GNSS stations. So, and for this project and installation of these corner reflectors, we did many experiments. So we first worked on the design of corner reflectors. We talked to the company, and finally they made for us, a Swedish company. And then we got 4 of these corner reflectors, passive ones. And in these pictures, you can see that since last year, December last year, we have been testing mostly at Morsbo that how to orient these corner reflectors, how strong is the signal. And here in the left, you can see this animation. These bright spots, so they show the location of the electronic corner reflector to the left. And there are 2 more, one permanently installed, and another one, it is just a simple one, just for some tests and so on. So we were orienting, and we were working on the strength of the signal and some RCS analysis and so we have been busy with that. And this is how it looks like, the permanent installation in Morsbo. And these are my colleagues in this picture, Rikard Jederberg and Nureddin Guido. That this is the mount or the mast, the metal mast. We put it on the bedrock, stable bedrock, and then we can install and orient this corner reflector to the satellite with the parameters we know in advance, we have calculated. And then we have also now the picture, what so far we have done. And these are 3 locations I mentioned to you. The blue ones, these are transponders, electronic corner reflectors, already installed during that geodetic SAR project. And still they are active, luckily. And we are going to continue with these transponders. And there are a few more passive corner reflectors we have installed. One of these yellow ones, which is now passive ones, it is in Morsbo. And then there are 2 more corner reflectors, which we made and sent it to Chalmers University. So Chalmers team, they installed it at Onsala Space Observatory, which is a famous geodetic observatory. They have different techniques, VLB, and they have GNSS permanent stations. and much more techniques that they can correlate all this data and get benefit of different technique results. And now InSAR also is coming to the family. And the good thing is now, I mean, at this location, you can see to the picture to the left, you can see, I mean, both ascending and descending tracks. And in the background, you can see the VLBI telescopes. So far, this is what we have done. And now, next week, we have planned for another one, a rectangular corner reflector ascending and descending. We are going to Norrköping. To the right, you can see the location, this GNSS station. And this will be another corner reflector, hopefully we will add to the network. So we have planned for 15 more passive corner reflectors for next year. And this will be actually great to have so many reflectors. And of course, I mean, it will come more and more, which they are very useful in different applications, as I mentioned to you, especially for this ground motion service. So that was what I had for today, and thank you very much for your attention.